So we're going to be doing about 3 types of sequence. Inductive sequences. We're going to be doing about arithmetic sequences and geometric sequences. So a lot to get through, so we'll get straight onto it. So as always, we'll just make a few notes. So if you want to copy this down, fair enough. If you just want to watch back later, I will also put the notes online. So the first type is inductive sequences. So an inductive sequence is a sequence in which we generate future terms from previous terms. So e.g., so the first type of the first example, we'll do u n plus 1 equals 3 un plus 2, where the first term I'm going to tell you is 2. And it's important, this won't work unless we define a first term. So we've got that u1 is 2. So what this says is the next term equals 3 times the previous term, 3 lots of un. Because we can see this is term n plus 1, this is term n, so this is one term before that one. 3 times the previous term plus 2. Like that. So if we're going to generate some of these terms, well, I've got that u1, the first term, is 2. And u is typically a letter we use to denote term with a little subscript. So term 1. Term 2 is 3 lots of the previous term, 3 lots of 2, plus 2, which is 8. Term 3 is 3 lots of the previous term, plus 2. So 3 times 8, 24, plus 2 is 26, and it goes on like that. And we can actually do this pretty quickly on our calculator as well, inductive sequences. So if I start by pressing 2, then equals, then 2 stored in the answer button. So now if I say 3 lots of answer plus 2, then press equals. Remember, 2 was stored in the answer button. Press equals. Now it gets 8. But now 8 stored in the answer button. So we'll press equals again. We get the next one, 26. And we can keep going. You can see it gets very big very quickly. So let's have a look at a question involving this. So I've taken a question 12 from the General Sequences worksheet, and I'm going to just pop that down there. We'll have a look at that. So it says a sequence is given by that recurrence relation there. The nth term is half of some value k plus 3 lots of the previous term. And notice I use letters subscripts n plus 1 and n. N plus 1 is 1 more than n. This is the same sort of notation, except they've used n to be the current term and n minus 1 to be the previous term. Both work. So a sequence is given by that recurrence relation there. Find an expression for u3 in terms of the constant k. Well, part A, we can see that u1 equals 2. So u2 is a half of k plus 3 lots of the previous term, is what that says, equals half of k plus 6 equals half k plus 3. So that's term 2. Term 3 equals, again, a half of k plus 3 lots of the previous term. And the previous term this time was half k plus 3. Let's simplify that. So a half of k plus 3 over 2k plus 9 equals, and let's simplify again, a half of, and k plus 3 over 2k is 5 over 2k plus 9 equals, so multiplying that out, we get 5 over 4k plus 9 over 2. So we've got an expression now for U3, just like it asked. So now part B, it says given that U3 equals 7, so we're told that this equals 7, find the value of k and the value of U4. Okay, so 5 over 4k plus 9 over 2, the third term, we're told equals 7. So if we times both sides by 4, we get 5k plus 18 equals 28, which means that 5k equals 10, which means that k equals 2 is the answer. So now it's saying find the value of the fourth term. Well, we can see that this formula still applies, but now we know that k is 2. So therefore, un equals a half, and k is 2 plus 3 un minus 1. Which means that, and let's have a look at U3 now. We can get a number for U3, which we're told is 7. U3 equals 7, which means that U4 is 1/2 of 2 plus 3 lots of the previous term, which is 7, equals, I think we can shove that straight in the calculator. So 21 plus 2 is 23 over 2 is the answer. There we go. Right, so that's inductive sequences, and there's not much more to those. I've got a lot of exam questions on the website in the free exam questions section, and on the worksheet that I've put online, the inductive sequences worksheet in the lesson area, you can get those as well. So do loads of questions on that. But let's now have a look at arithmetic sequences. So an arithmetic sequence is a sequence of numbers with a common difference between terms. So a common difference between terms. So an example would be 2, 5, 8, 11, and so on, common difference of 3. So I don't think we need any more examples of that. And the nth term of a sequence, such as this, well, the first term is denoted by A, usually. The difference between terms is denoted by D. So the nth term formula, UN, equals A plus n minus 1 D. And that's a formula that you need to remember. That's not given in all the different exam boards formula books. So you should be able to remember that and use it. But what I want to do first of all is just prove why it's that. Well, the first term is A. The second term is A plus D. The first term plus a difference. The third term, A plus 2D. All the way to the nth term, A plus, and notice that this number here, the number of differences we add, is always one less than the term number. So sort of intuitively proved it. A plus n minus 1 D. So that's the nth term of an arithmetic sequence. But say that I wanted to sum the different terms. So sum arithmetic sequences. And the sum of a sequence is also called a series. So you'll quite often see it being called a series as well. A series is when we sum terms. So a series is when we sum terms of a sequence. So let's say we've got 2, 4, 6, 8, and so on. That's a sequence, a list of numbers. As soon as we start adding the terms together, 2 plus 4 plus 6 plus 8, and so on, that becomes a series. So the act of adding a sequence makes it a series. And the formula, which you are given on your formula sheet in an exam, formula for summing arithmetic series and you should remember this, but you don't need to, is a half n 2a plus n minus 1 d, where a is the first term, d is the common difference between terms, and n is the number of terms being summed. And that there is an absolutely key formula. So if you are making notes, highlight that. And this here, really important. So we'll do an example. So half n, 2a plus n minus 1d. So we'll do an example. e.g. find a formula for the nth term of the sequence 10, 13, 16, 19, and so on, and find the 20th term and the sum of the first 20 terms. So what we're going to use is the two formulae that we used before. We've got the nth term formula there, and we've got the sum of n terms there. So the first part is to identify what the nth term would be. So we can see here that the first term is 10, and the common difference we can see between terms is 3, goes up in threes. So the nth term, un, equals, and we saw it up here, a plus n minus 1d, a plus n minus 1 d. And there's our formula, which needs to be simplified. 10 plus 3n minus 3 equals 7 plus 3n. You can always check that that works by subbing in values of n. So n equals 1 gives 10, first term. N equals 2, 7 plus 6 is 13. Yeah, that looks right. So we found the nth term. So let's conclude properly. Therefore, un equals 7 plus 3n. So then it asks to find the 20th term. So we denote that with u20. This little subscript is the term number. Equals 7 plus 3 lots of 20. Which is 67. That's the 20th term. And then the sum of the first 20 terms. So we're going to use this formula here. Sn equals a half n, 2a plus n minus 1d. So we've got here that a is 10, d is 3, and it's the sum of the first 20 terms. There's 20 terms in the sum. So I'm going to denote that by writing S20, where there's a 20 in place of the n, equals a half n, 2a plus n minus 1 times the common difference d, and that's really one for the calculator. So a half n 2a plus n minus 1 d equals 770. And there's a way on your calculator that you can check these answers using the summation button in the top right. So top right gives you that. And we've got an nth term for it. It was 7 plus 3n, except the calculator uses x. 7 plus 3x. And we want all the terms between 1 and 20, which should give us exactly the same answer. So yeah. So we can actually use that button as well to check our answer. And it's actually, unless the question says show full working or show detailed reasoning, it's fair game just to use that function on the calculator. But there actually is an alternative formula as well that we can use. So it's also given in the formula sheet, and it's sometimes quite useful. So alternative formula. So Sn equals a half n a plus l. where A is the first term in the sum, L is the last term in the sum, and N again is the number of terms being summed. So let's take the previous example and just do the question again. So say that I want to find, e.g., find the sum of 7 plus 3x. That's what that sigma notation means, the sum of 7 plus 3x. And we want to go from the first term, x equals 1, all the way up to the 20th term. So that's saying sub in x equals 1, sub in x equals 2, sub in x equals 3, sub in x equals 4, all the way up to x equals 20, then add all your answers together. So the first term in this sequence, we sub in x equals 1, is 10. The last term, if we sub in x equals 20, 67. And I can see here we want to sum 20 terms. So the sum equals a half n a plus L. Putting that in the calculator. A half n a plus L equals 770 also. So though you could be expected to use both formulae, I prefer the longer formula that we used before, but this formula can be useful as well. So again, answer is 770. So I think it's good to do a bit more of an applied question now, because those first couple seem quite straightforward. So let's try this one from the worksheet. So this is question 10 from the Arithmetic Sequences worksheet that's in the lesson area. So let's have a look at this one. So the third and eighth terms of an arithmetic series are 72 and 37 respectively. Now, I think good technique for a question like this is to write down the information mathematically as you're given it in the question. So the third and eighth terms of an arithmetic series are 72 and 37 respectively. So the third term, well, the formula for the third term is a plus 2 lots of difference, a plus n minus 1d, where n here is 3. So the third term, a plus 2d, equals 72. And the eighth term, a plus 7d, is 37. So if we solve, and I'm guessing we're going to have to solve these equations simultaneously. Let's have a look. So part A, find the first term and the common difference of the series. Yeah, the first term, A, and the common difference. So you could go back to GCSE and solve those equations simultaneously using the elimination method. However, it is fair game in A level to use your calculator to solve such equations unless the question says show full working. So let's take advantage of the fact we've got the calculator, solve the simultaneous equation, 2 unknowns, and it's 1a plus 2d is 72. 1a plus 7d equals 37. And as I say, it is fair game just to put those in the calculator and let that solve it for you. So x equals 86, and x was a. So a equals, what did we say it was? 86. And d equals, so make use of all the tools available to you. The common difference is minus 7. So we've got that from just using the calculator. If it says show full working, then you can't do that. But because it doesn't say show full working, we are allowed to use the calculator. And part B, find the sum of the first 25 terms of the series. So S25. But in this case, A, the first term, was 86. D is minus 7. And it was 25 terms we wanted to find. So N equals 25. So it's a half N 2A plus N minus 1, common difference, equals, straight in the calculator, so a half N 2A plus N minus 1 D equals 50. Again, to check that in the calculator, use the sum. So it was A plus N minus 1 times minus 7 is the nth term, A plus N minus 1D. We want all the terms from 1 up to 25. Yeah, 50. And that's that. So what I'm going to do, I'm going to leave you for a couple of minutes to do another question. So take 3 or 4 minutes on this. But another one along the same lines. Slightly more challenging. Because it tells us here the fifth term of an arithmetic series is 23. So we dealt with that in the previous question. And the sum of the first 10 terms of the series is 240, different formula. That's the only clue I'm going to give you. I'm going to leave you to it for a little while. I'll have a go at it in just a moment. So to start this off, part A, so it says the fifth term of an arithmetic series, the fifth term, so A plus 4 differences equals 23, and the sum of the first 10 terms, S10, and we know the formula for that, a half N 2A plus N minus 1, which is 9, D. And I think the key before moving on is to simplify that. So half times 10 is 5. 2A plus 9D equals, so that's 10A plus 45D, and we're told that that's equal to 240. So now we've got two simultaneous equations again. got this one here and this one here. And as I said, it is fair game to just put in your calculator. So, straight on the simultaneous equation solver. Two unknowns. So we've got 1a plus 4d is 23. And 10a plus 45d is 240. So x equals 15. That's a is 15. And d is 2. So we found the first term and the common difference as asked. Part B, find the sum of the first 60 terms of the series. So S60. Well, the first term we found to be 15, the common difference 2, and the number of terms we're summing is 60. So using the formula, we've got a half n, which is 60, 2a plus n minus 1 d. So half n 2a plus n minus 1 d equals 4,440. So that's how to tackle questions like that with arithmetic sequences. I think now let's have a look at some geometric series. So we'll move on to geometric series. So geometric series, or geometric sequence rather, is a sequence of numbers which has a common multiple also called ratio, between terms. So an example would be 3, 6, 12, 24, 48, etc. So doubling each time. So the ratio between terms here is 2. And we'll get straight on to the formulae for geometric sequences. So the nth term, un, and you aren't given this in many of the exam board's formula booklets, un equals a r to the power of n minus 1. And the justification of that, I'll just do it at the side here. So the first term is a. To get the second term, you times a by the common ratio. To get the third term, you times by the common ratio again. First term, second term, third term, all the way to the nth term, AR. There's always one less ratio than the term number. So again, another justification of why. The sum of the first n terms, and you are given this in the formula booklet, and I have proved this formula in one of my YouTube videos, so you might want to have a look at that on the YouTube channel. 1 minus r to the power of n over 1 minus r. And if we sum an infinite number of terms, formula just becomes a over 1 minus r. But the sum to infinity, the only way that the sum to infinity of a sequence will work is if the common ratio is less than 1. The size of the common ratio is less than 1. Also, that can be written as ratio has to lie between 1 and minus 1. So the modulus of the common ratio has to be less than 1. Both of these statements are equivalent, but that must be the case for the sum to infinity to work. The reason is, if we sum terms in a sequence, say 1 plus 2 plus 4 plus 8, if we keep on summing those forever, the number's just going to get bigger and bigger and bigger. It's going to go to infinity. So any common ratio bigger than 1 makes the numbers get bigger. Therefore, the answer isn't going to settle to a constant value. It's just going to keep getting bigger and bigger. Whereas if I had a ratio a half, let's say 1 plus a half plus a quarter plus an eighth plus a 16th, the numbers are getting smaller and smaller. Eventually, we're going to be adding something close to 0 on. So it's going to settle to a constant value. So when the ratio is less than 1, and between minus 1 and 1, then we do get a sum to infinity. And when it does settle, so when modulus of r is less than 1, the sum to infinity is said to, and here's a key word, converge. So let's have a look at this in the context of questions again. So let's say, I'll put this from a worksheet up. So I'm looking at the geometric sequences worksheet. I'm putting question 6 on here. So the second and third terms of a geometric series are 2 and 10 respectively. Okay, the second term is AR. So AR equals 2. And the third term, AR squared, equals 10. Find the common ratio of the series. So I'm going to call this equation A and this equation B. So when we went back up here, I know I used the calculator for this, but what we would have done, we would have subtracted one equation from the other. We would have done bottom take top to get 5D equals whatever 37 minus 72 is, and the A's would be eliminated. We're going to do something similar here, but because the simultaneous equations don't involve adding variables together, they're actually times together. A is multiplied by R rather than added to a multiple of R. We're going to do something a bit different. So what we're actually going to do is take the highest power equation here, the highest power of R, and divide that equation by this one here. So we're going to, rather than add or subtract equations, we're going to divide. We're going to do B divided by A, and I've chosen B because it has the highest power of R, and you'll see why in a second. B divided by A equals, or rather implies, so the left hand side becomes AR squared over AR, and the right hand side becomes 10 over 2. And we can see that a little bit of cancellation happens there. A divided by A is 1, so we might as well not do that. And R squared divided by R is R equals 5. So by dividing those two equations, and this will work when you're given similar pieces of information in a question like this, this will work every time. Dividing one equation by another will eliminate A. So we've found the common ratio. So that's part A. Part B, find the first term of the series. Well, we've got AR equals 2, and now we know R, which means that A times 5 equals 2, which means that A equals 2/5. And then part C, find the sum of the first 8 terms of the series. Well, again, you could look at your formula booklet, but it's this formula here. We're going to use the sum of the first 8 terms So we've got A equals 2/5. R equals, we said, was 5. And the number of terms that we're summing is 8. So the sum of the first 8 terms equals A. 1 minus R to the n. So 5 to the power of 8 over 1 minus R equals, so putting that in the calculator, fraction button first, and then we've got another fraction as well actually, so 2/5 bracket 1 minus 5 to the power of 8 over 1 minus 5 equals that there, 39062.4. Okay, let's have a look at another question. I'm going to put question 9. And you can have a go at this one. So have a go at that. I'll give you a couple of minutes, then I'll go at it. Okay. So the first and third terms of a geometric sequence, geometric series are 6 and 24 respectively. So let's put that information in maths. So it tells us the first term is 6, and the third term, AR squared, equals 24. Find the two possible values for the common ratio of the series. So take the one with the highest power of R, then divide it by the other one. B divided by A equals, or rather implies, so we've got AR squared over A equals 24 over 6. They cancel to give R squared equals 4, which means that R is equal to plus or minus 2. Part B, given also that the common ratio of the series is positive, find the sum of the first 15 terms of the series. So we know that R is 2 now, and we've got A equals 6. And we want the sum of the first 15 terms, so n equals 15. So S15 equals A, 1 minus R to the power of n over 1 minus R. Straight in the calculator. Six, 1 minus 2 to the 15 over 1 minus 2. 196,602. there's our answer. So let's have a look at another question, maybe one involving the sum to infinity. So I'm going to take question 18 from the sheet. So the common ratio of a geometric series is 0.55 and the sum to infinity of the series is 40. So before you even read the rest of the question, I would write that down in maths. So take a moment, write down that information in using mathematical notation. You might look back up at your formulae. So the common ratio (0.55) and the sum to infinity a over 1 minus r is equal to 40. Which means that, and it said find the first term of the series now, so part A, find the first term. Well, we've got from this information here that a over 1 minus r equals 40, which means that a equals 40 times 0.45. Times 0.45 equals 18. So the sum of the first term is 18. Part B, bit more difficult. So find the smallest value of n for which the nth term, stop reading, write the formula for nth term, ar to the n minus 1, is less than, for which the nth term of the series is less than 0.001. Well, we've got the values of a and r now. This implies that a, which is 18, times r, which is 0.55 to the power of n minus 1, is less than 0.01. Now this is going to involve logarithms to solve, and we've got a choice of bases. You could use log of base 0.55, but any base between 0 and 1 would involve the inequality sign flipping. And that's just a rule to remember. Any log of base between 0 and 1 flips the inequality sign. I would actually use ln in any case, just because it's on the calculator. There's a button ready for it. There. I would just use ln because it's quicker and easier. But we're not ready to log both sides yet, because this 18 is still attached to our exponential part. So what I'm going to do is divide by 18 first, which means that 0.55 to the power of n minus 1 is less than, and 0.001 divided by 18 gives, we'll keep it as that one there, 1 over 18,000. And if we log both sides now, log base e, which is ln, so I'm going to log both sides, ln of 0.55 to the n minus 1 is less than log of 1 over 18,000. And what I'm going to use now is the power rule for logarithms. So that power can jump down to the front. It's equivalent to do that. And one thing you've got to remember here is that n minus 1 is in brackets. It's all of that n minus 1 that's attached to the front. And in a lot of the exam boards, if you don't put brackets around that, the n minus 1 at the front, then it can take the rest of the marks from the question away from you for incorrect working. So ln 1 over 18,000. So it's very important to have brackets around that n minus 1. Now I'm going to divide by log of 0.55. So n minus 1 is less than log of 1 over 18,000 divided by log of 0.55. Something strange has happened here because this line that I've just written is incorrect. And the reason that it's incorrect is because ln of any number between 0 and 1 is negative. So actually, I need to flip the inequality sign. So always look for dividing by logs of numbers between 0 and 1, because it would flip an inequality sign the other way around. Then finally, n is greater than 1 plus log of 1 over 18,000 over log of 0.55, which is equal to 1 plus log of 1 over 18,000 over log of 0.55, 17.389. So we can conclude that n has to be bigger than 17.389. But looking carefully back at the question, find the smallest value of n. N has to be an integer because it's a term number. So n, the smallest value of n, is the first integer that satisfies this inequality here. So if n is bigger than 17.389, then the smallest it could be is n equals 18, and then we're done. So that's that question. But I'd quite like to do something in an exam context before we finish. So let's have a look at a mixed question. So this one I'm taking from my exam questions off my website in the exam questions by category section. Just take a moment to digest that. So Jamie's trained for a triathlon, which involves swimming, running and cycling. On day 1 he swims 2 kilometres, then swims the same distance on each subsequent day. So he always swims 2 kilometres every day. On day 1 he runs 2 kilometres, and on each subsequent day he runs 0.5 kilometres further than on the previous day. So 2.5 kilometres on day 2, 3 on day 3, and so on. So that's a particular type of sequence that you should notice. There's a common difference between terms. So annotating this, and this is what I would do in an exam. Annotating this, I would write arithmetic. And on day 1, and the difference, as I say, just annotating it for now, A equals 2, D equals 0.5. So then for cycling, on day 1 he cycles 2 kilometres, and on each subsequent day cycles a distance 10% further than on the previous day. So we can see that it's being multiplied by something each time if we're going up in percentages. So it's geometric, where the first term is 2, and the common ratio, you'd be forgiven for saying 0.1, but it's actually 0.1 further. So to get 0.1 further, we times by 1.1. So find out how far he runs on day 15 is the question from part 1. So part 1, we're talking about running. So running is the arithmetic sequence. So A is 2. The common difference is 0.5, and the term number was day 15. Now be careful to choose the correct formula here, because it could easily go wrong. So the question hasn't asked us to sum the total distance that he's ran over the 15 days. It just asks how far he runs on day 15. So that's the nth term rather than the sum formula. So U15 equals A plus n minus 1 D equals, and half of 14 is 7, so 2 plus 7 is 9, and let's give the units as well. 9 kilometers he runs on day 15. Part 2. Verify the distance he cycled in verify that the distance cycled in a day first exceeds 12 kilometers on day 20. Well, let's have a look at day 19 first. If we're verifying that it first does that, we should show how much he cycles on day 19. So this is the geometric sequence if we're talking cycling. So n equals 19, a equals 2, and the common ratio is 1.1. So U19 equals a, which is 2, times r to the n minus 1. So 2 times 1.1 to the power of 18, which is 11.11 kilometers, which clearly is less than 12. Now let's look at the 20th day. 2, 1.1 to the 19 equals 12.23 kilometers, which clearly is greater than 12. Therefore, the conclusion will be appropriate. First exceeds 12 kilometers on day 20. Part 3. Find the day on which the total distance cycled up to and including that day. And there's the key word there, total. So that indicates what formula we're going to use. First exceeds 200 kilometers. Have a go at that yourself. Take a couple of minutes. Write the correct formula down. Write the correct inequality down and try and solve it. So it's very similar to the previous example that we did just here, except it uses a different formula. So have a go at part 3. Find the day on which the total distance cycled up to and included the first day first exceeds 200 kilometers. Look at what type of sequence it is. Use the correct formula and rearrange. So it's the geometric sequence because it's the cycling. So S20 equals A 1 minus R to the power of N over 1 minus R. And we want it to exceed 200 kilometers. So now if we times both sides by 1 minus 1.1, i.e. minus 0.1, we get 2, 1 minus 1.1 to the power of n, and 200 times minus 0.1 is minus 20. But remember, we've had to multiply by a negative number, so that changes the direction of the inequality sign. Divide by 2. Means that 1 minus 1.1 to the n is less than minus 10. Take 1. Minus 1.1 to the n is less than minus 11. Times both sides by minus 1 to get both positive numbers. 1.1 to the n, and remember again, flip the inequality since we've times by a negative number. It's greater than 11. Then log both sides. ln of 1.1 to the power of n is greater than ln of 11, which implies that n ln of 1.1 is greater than ln 11 using the power rule. So that what I've done there, the power's jumped from there to the front. Divide by ln of 1.1, which means that n is bigger than ln 11 over ln of 1.1. ln of 1.1 isn't negative because it's not an ln of a number between 0 and 1. So that's equal to, so log of 11 divided by log of 1.1 equals 25.159. So n has to be bigger than that. Therefore, n equals the next integer up, 26. So now find the total distance travelled by swimming, running and cycling up to and including day 30. So I'll just put this back up here. So 3 sequences that it wants you to find S30 for. I'll give you a moment to do that. So it wants the sum S30 for each of these 3 sequences. Take a moment, get that done. Put the question down here. Well, the first sequence is nice and easy, just 2 times 30. Sequence 2, using the formula S30 equals a half n 2a, and in this case a is 2, the first term of the sequence is 2, plus n minus 1 times the common difference between terms, which is 0.5. So a half, 30, 2a plus n minus 1 d, which is 277.5. And then finally, the third sequence, which is the geometric, which is a 1 minus r to the power of n over 1 minus r straight in the calculator. A 1 minus r to the power of n over 1 minus r 328.988. Then summing all of those, therefore total equals 60 plus 277.5 plus 328.988 equals 60 plus 277.5 plus that, which is 665.988. Yeah, equals 665.988 kilometers. And there's our answer. So that's a quick journey through arithmetic, geometric and inductive sequences. I suggest you do all the questions on the worksheets to get good at this. And I would suggest also that you have a look at some of the exam questions on my website to get it done. But yeah, that's sequences. So check the schedule for what the lesson's going to be on next week.